Hello class, this is the second part of the lesson 5.6 about the second derivative and the concavity of a function. And we're going to continue with the examples 2, 3, and 4. Remember that the first example I gave it to you in the first part of this lesson. So let's see, it's the same instruction. Use the second derivative to investigate the concavity of the following functions. And we have these three functions. Please pause the video and write them down. Okay, let's continue. So, example 2, we have this function. Okay, we're going to start easy again. So, this function is x to the cube. And remember, the first step is getting the second derivative. Okay, so let's start with the first derivative. F prime of x equals 3x squared. And next, the second derivative is going to be equal to 6x. So there you go. And in here, I'm going to take a few seconds to make a correction because I have been mispronouncing something. A very important correction. If you notice, this symbol, and I've told you that this symbol is read as F prime. This little apostrophe here is read prime in mathematics. F prime of x equals etc. And in Spanish, in Latin America, the way we read this symbol, this one, is f b prima de x. F b prima de x es igual a 6x. Así se hace en español, al menos en Latinoamérica. Okay, let me go back to English. The problem is that I assumed that in English it was the same idea, okay, f b prime or bi prime, and that's the way I have been pronouncing it, and that's the way you have been hearing it. Now, I got curious about whether in fact that's the way people in the United States or anywhere else say it, and no, I could not find anyone pronouncing this as f b prime or bi prime. At least I could not find it. So I'm gonna assume that they don't use this form of language, and so we're gonna stop calling it f bi prime or fb prime unless in sometime in the future I actually notice that that's in fact correct. Okay, so that was the correction. So how do we call this, or how do we read this? The second derivative of f of x. I know that's that's a lot of stuff, but anyways. Okay, so that's the first step. Second step, make the second derivative equal to 0. Why? What for? Let me continue here. In order to find possible inflection points. Underline this word, it's very important. And so let me make my second derivative equal to 0. Very simple equation to solve. 0. So this is my possible inflection point. Okay, number 3. Step number 3. Evaluate the function. No, sorry, that's the second derivative of f in the intervals that are created by the inflection point. by the inflection point. What do I mean? I mean this. If we lay down our Cartesian system, my possible inflection point is right there at the origin. Okay, and as you remember, your inflection points or also your turning points divide or partition your whole x-axis into intervals. In this case, the interval from minus infinity to 0, that's the first interval, and the second interval goes from 0 to plus infinity. So I'm gonna write, okay, my first interval will be from minus infinity to 0. My second interval goes from 0 to infinity. And I want to evaluate my second derivative in any point that I place. I'm going to evaluate in x equals minus 1 and in x equals 1. Remember, any choice works as long as is within the interval that you're analyzing. So for the first interval, I'm going to choose minus 1, and I'm going to evaluate my second derivative in such number. What is my second derivative? It's 6x. So I'm going to plug the minus 1 right there, and I'm going to get minus 6. And so the sign of the evaluation is negative, and that tells me, what that tells me is that over this interval, my function is concave downwards, downwards, downward. Okay, and we do the same with the other interval. We evaluate in 1, I said. We're going to get 6 times 1, which is 6, which is positive, and which tells me that my function over the interval from 0 to infinity, my function will be concave upward or upwards. And that's it. We are done. What is my conclusion? Let's write down a proper conclusion over here. It's not absolutely necessary, but it's always a good idea. Okay, we can write this. F is concave upwards. No, I'm sorry. Concave downwards over minus infinity to 0 and concave upwards over the interval, I'm sorry, 0 to infinity. Okay, so basically we're gonna have, since I already know how this one looks, it's gonna look like, and I suppose you too know how the graph of this function looks. It looks like so, right? If you remember, it's a very common graph. You should memorize the graphs of the most common functions, and x cubic looks like this. And does that satisfy our conclusion, or does that match our conclusion? Yes, because you can see that from minus infinity to 0, the concavity is downwards, you see? And from 0 to plus infinity, we get concavity upwards. Let's check. There you have it. You see? Concavity downwards first, and then concavity upwards. So it checks. So you see, it's not difficult, guys. It's actually quite simple once you get the knack of it. Okay. Second example. I'm sorry, third example. F of x equals x to the fourth. Okay, I'm gonna do this one a little quicker. So get f the second derivative, and so let's do it. The first derivative is this, and the second derivative is 12x to the square. Okay, make second step, make f I always I always want to say f by prime, but I can't. Make the second derivative equal to 0. So what is my second derivative? It's this, okay? And my solution to such equation is again 0. So this is a possible inflection point. Possible inflection point. Let's continue over here. Step 3, evaluate second derivative over the intervals. Over the intervals. Well, I'm not going to continue the other thing, okay? You already know what I was going to write in here. So this is my x-axis, this is my y-axis. My inflection point occurs right here. Let's choose 2 points, one to the left, one to the right of such inflection point. One more time, I'm going to use simple integers for simplicity. And what are my intervals? My interval number 1 goes from minus infinity to 0. My interval number 2 goes from 0 to infinity. Let's evaluate the second derivative if in my chosen numbers. And you're gonna get, the second derivative is this, right? So you're gonna get 12 times minus 1 to the square, which is 12, which is positive. And that means concavity upwards, okay? And the second derivative evaluated in 1, you're gonna get 12 times 1 to the square, which is 12, which is again positive, and we got the same concavity upwards, okay? So conclusion, again, I'm just gonna say it. I'm not gonna write it down because I lose a lot of time. What is my conclusion? Well, this is not this this x equals 0, this point that was a possible inflection point is not an inflection point. This point is not an inflection point. Why not? Because my function is not changing the concavity. To the left of this point, it's concave upwards. To the right of this point is also concave upwards. And remember that the definition or the concept behind behind an inflection point is that your function should change concavity. And if that's not the case, we cannot say that this is an inflection point. So it's not an inflection point. Okay? And that's it. What's my conclusion? Well, I'm gonna say it very quickly. Over the interval 1 from minus infinity to 0, my function is concave upwards. And from 0 to infinity, my function is also concave upwards. Or basically, we can say that the function is always concave upwards. Done. We are completed. Now let's see how that looks. Remember the function f of x equals x to the 4. And look, you see? You see why? From minus infinity to 0, the concavity is upwards, as you can see. But also from 0 to infinity, my concavity is also upwards. You see, so this function is always concave upwards. And that settles the whole thing. Oops. Okay. Now, let's do the last example. Okay. The last example was this one, a little more complex. The function was 1/12 times x to the 4 plus 1/3 times x to the 3 minus 3/2 times x to the 2 plus x plus 1. Okay, let's do it. First thing, get f by prime. I'm not gonna do it, I'm just gonna write it down. You can pause the video, get it on your own, and you will see that the second derivative will be x squared plus 2x minus 3. Okay, so this is my first step, getting the second derivative. Second step, make the second derivative equal to 0 in order to locate or in order to find the possible inflection points, right? So this is my second derivative. This equation is a quadratic equation. We can solve it. In this case, we can solve it through factorization. And so your two values will be x equals minus 3 and x equals 1. So these 2 points are my possible inflection points. Possible. Okay, let's continue. Step number 3, same idea, evaluate the second derivative over the intervals created, writing very randomly, over the over the no, I wrote that, sorry, over the intervals created by the possible inflection points. Okay, so you see by now, I guess you already know the whole thing, right? Okay, my first interval. Well, let me locate my possible inflection points over my x-axis. It's gonna be minus 3 first. Let's put it over here, and 1 should be or over here more or less. X equals minus 3 and x equals 1. And then so we have three intervals, right? We have from minus infinity to 3. I'm sorry, from minus infinity to minus 3, and then second interval from minus 3 to 1, and the third interval from 1 to infinity. So my first interval goes from minus infinity to minus 3, like I said. My second interval goes from minus 3 to 1, and my third interval goes from 1 to infinity. Let's choose some points over those intervals. Let's choose minus 4 for the evaluation, right? Let's choose 0. Always choose 0. That makes your life simpler. And let's choose x equals 2. Okay, so let's do it. Let's perform the evaluations of the second derivative over these three numbers. If the second derivative on minus 4, the second derivative evaluated in 0, and the second derivative evaluated in 2. Okay, let's do it. I'm not gonna do the whole thing. I'm just gonna, again, pause the video, do it, and then I'm just gonna write down the final evaluations. So we're gonna get we're gonna get 5 in here. In here we're gonna get minus 3, and in here we will get 5 again. This is just a coincidence, okay? 5 and 5, just a coincidence. Okay, so what can we observe? That the evaluation of the second derivative over this interval is positive, and then negative, and then positive. So that means that in fact my function is changing concavity as it goes through the intervals. In this interval, it's concave upwards. In this interval, it's concave downwards. And in this final interval, is concave upwards again. So, conclusion, these 2 points, again, you should write it down, okay? I don't want to do it because it takes me a lot of time, and there's no point in you seeing me writing, okay? But my conclusion is this: these 2 points that were possible turning points are in fact turning points, 100% sure. Why? Because they signal a change in concavity as demonstrated here. Okay, the change in concavity of my function. It goes from concave upwards to concave downwards to concave upwards again. And that's it. My function is concave upwards over this interval, concave downwards over this interval, and upwards again over this interval. And these 2 points were in fact inflection points. And that was the whole purpose of this task, getting getting that information. Okay, so let's see how this looks. Remember, concave upwards, downwards, and then upwards again. And the inflection points are -3 and 1. Write those down. And let's see how it looks. This is the function. You see? So, like I said, it's first concave downwards. It's over this all that I'm all the line that I'm tracing now. All of this part is concave downwards, more or less at about here, more or less. Okay, but according to my analysis, it's actually this number, -3 right here, right there. This is the point. This is the inflection point. -3, comma, its proper corresponding y, right? So right there, at that point, my function changes concavity, and now it's gonna go concave. I'm sorry, I said concave upwards first. I think I said downwards. Sorry, I don't know what I said. First is concave upwards, and then at three over here, it changes to concave downwards, and at 1, right over there, right there, right there, it changes again to concave upwards, just like we said. Upwards, downwards, upwards. You see? Upwards, and then downwards, and then upwards again. And now you know the points of inflection. So that's it, guys. I hope you have understood this concept of the second derivative and how we use it in order to get the concavities of a function. And pay attention to this example, okay? Not all inflection points. Remember that this was no, this was a possible inflection point that turned out to be not one. So pay a lot of attention to that. Okay, so that's about it, guys. Now get to work on the workbook, and that's it. Thank you so much. Any questions, please address them to me via private message. So see you guys.